kinds of chemical bonding. We've seen ionic bonding between a metal and a non-metal, and when they come together in a bond, the non-metal actually steals electrons away from the metal. We get ionization. And we've looked at non-metal to non-metal examples where the two atoms have a very similar electronegativity, and therefore they end up sharing the electrons by default. The tug of war for electrons ends in a draw, and they have to share electrons to complete octets. And what we're going to see in the next hour is that we also have a middle ground area, what we sometimes refer to as polarized covalent bonds. Chemical bonds where the electrons are actually being shared unevenly. And somebody has a little bit of an upper hand, but not enough to outright steal the electrons from the other atom. So we have to make comparisons of electronegativity for that. And just a reminder, as we saw before, electronegativity increases as we move across a row of the periodic table, because we're looking at elements and atoms with more protons without a change in the shell number. More protons, a greater pulling power. And the second trend we saw was moving from the bottom of any particular column towards the top of the table. Again, the electronegativity increased, despite a decrease in the number of protons. But the removing of layers, the removing of shells, meant that those electrons in the last layer were much closer to the nucleus at a smaller and lower energy level. So that reduction in the energy gap to the nucleus was much more significant, and we see an attraction which is getting stronger as we move up the table with fewer shells. So all the elements which were good at attracting electrons were the non-metals in the top right-hand corner of the periodic table. The electronegativity of the elements has been measured for quite some time. You would never be expected to know individual electronegativities. You should know the trend as we move from left to right, getting bigger, and the trend from the bottom towards the top. You wouldn't be expected to know any particular value. So a table like this would always be provided for you if you needed a check. So when working out whether we have ionic bonding or we have covalent bonding, we look at the difference in electronegativity of the measured elements. And we say that for elements with a difference in electronegativity less than 0.5, we say that those atoms are truly covalently bonded together. They are sharing electrons in their outer shell. And when the difference in electronegativity is greater than 1.9, huge big difference, a difference big enough so that one of the two atoms is actually stealing electrons away from the other, the non-metal stealing electrons away from the metal, we say that it's a truly ionic bond. And the ions are held together because of the opposing electrostatic charges, positives and negatives. Opposites attract. But then we have this middle ground, when the difference in electronegativity is greater than 0.5, but isn't as great as 1.9. So between 0.5 and 1.9, one of the two atoms has the advantage. One of the two atoms is pulling the electrons away, but isn't able to completely steal the electrons away from the metal atom. So these examples, when the difference is in this middle range, this is what we refer to as polar covalent bonding. Atoms which are sharing electrons, but sharing them unevenly or unequally. And when things aren't shared evenly, it's still going to lead to mild electrostatic charges. So on page 102, we have some examples. Carbon to hydrogen, sulfur to carbon, boron to phosphorus, phosphorus to hydrogen, all examples of elements with differences in electronegativity less than 0.5. And so the atoms are pretty much sharing those electrons evenly because they have a similar strength of electronegativity. Meanwhile, we have examples between metals and non-metals primarily, with a difference in electronegativity, just a sheer difference. There's no positive or negative to the answer, just a sheer difference in electronegativity. These elements, when combined, they produce ionic bonds. Because one element steals the electrons from the other to create positive and negative ions. Yes?
What if it is exactly on 0.5 or 1.9?
So we've got to draw the line somewhere, and the reality is, if there is a difference in electronegativity, even if it's just 0.1 or 0.2 of a difference, they're not equally sharing the electrons. Somebody does have the upper hand. But when the electronegativity difference is so small, we say it's so negligible, they're pretty much sharing electrons evenly. When we get up to 0.5, it's getting, we think, to a fairly significant threshold. So if the value is exactly on 0.5, I don't mind for the test whether you declare that to be non-polar or polar covalent. Okay, that's right on the line. And again, the reality is, if there is a difference, then it's not equal sharing. But up until about 0.5, we don't consider it to be really significant. But 0.5 and higher, up to 1.9, that difference in electronegativity means that one of the two atoms in the chemical bond is pulling on the lion's share of electrons. Atoms which have a greater slice of electron density are negatively charged. So we say in these examples, the chlorine, the oxygen, and the oxygen again, with hydrogen this time, we say that they're electron enriched because they're pulling and taking the lion's share of the electrons in that chemical bond. Yes?
I think I figured it out.
Okay. Meanwhile, the atom which is losing in that tug of war, the hydrogen, the carbon, and the hydrogen again, now this time with chlorine, these atoms which are losing that tug of war for electrons have been made to feel slightly electron deficient. So we say that they have a mild positive charge on them. So chemical bonds, covalent bonds with unequal sharing of electrons, these polarized bonds, like poles of the planet on opposite ends of the planet, we've got poles of electron density. One side which is electron intense, and one side which is electron deficient. So we say that across the bond, a dipole appears in that bond. So one end is electron enriched, and one end is electron deficient. A dipole bond or a polar covalent bond. Now we can show these dipoles in a diagram by drawing an arrow pointing towards the more electronegative atom. The arrow is pointing and showing where the electrons are headed. The electrons are being pulled towards the more electron-enriched atom. On the other end of the dipole, we put a little cross through the other end, because if we look at that end and take off the arrowhead, it looks like a little positive sign. So it's mimicking the positive nature or the electron deficient nature of the less electronegative atom in the bond. We sometimes use little delta symbols, the Greek delta symbol, delta positive or delta negative, delta positive, delta negative. Again, to reinforce that idea of one of the atoms getting the lion's share of the electrons and one of those atoms losing out, feeling electron deficient. So there's mild charges associated with these dipole bonds, positives and negatives. But it is nowhere near as strong as a proper ion bond. Again, it's like comparing static electricity, putting a comb through your hair, comparing it to electricity coming out of the wall. Much different amperage and voltage. Basically the same thing, electrons with different order of magnitude. And these dipole bonds are again a much smaller order of magnitude compared to ion bonds. But it's still the same basic principle, positives and negatives. And when molecules are lined up next to each other, positive ends of a bond will be attracted to the negative end of another bond. So it can lead to chemical and physical interactions with matter. Positives and negatives, opposites attract. Paula Abdul always rings true. So where you have a molecule with polarized bonds, dipole bonds, that can lead to additional attraction with neighboring bonds and neighboring molecules. And it can greatly affect the properties of matter.